projects. In this video, we are going to explain about the project entitled as Advancements in Landmine Detection, Deep Learning Based Analysis with Thermal Drones. So before getting into the video, let me give you the brief description about the project. This project focuses on improving landmine detections by integrating deep learning algorithms with thermal imaging drone technology. By analyzing heat patterns and environmental cues from aerial data, the system aims to identify buried landmines more accurately and safely, reducing risk from ground personnel and enhancing the efficiency of demining operations. Coming to the abstract states that this project focuses on addressing the persistent threat of landmines in post-conflict regions by introducing a safer and more efficient detection approach using deep learning and thermal drone imaging. Traditional methods such as manual probing and metal detections are often slow, hazardous, and prone type of false positives, creating the need for more advanced solutions. In response, the project proposes a framework in which thermal drones capture temperature variance on the ground and neural network model analyze these patterns to identify potential buried landmines with greater accuracy. By combining aerial thermal sensing with automated deep learning analysis, the system aims to reduce human explores to dangerous environments, minimize false detections, and significantly enhance the overall speed and reliability of demining operations. Coming to the existing system, the existing landmine detection systems rely heavily on manual or semi-automated methods such as metal detectors, ground penetrating radars, trained animals, and human operators. Although these techniques can be effective in certain conditions, they face several critical limitations. They are slow, expose personnel to dangerous environments, and often fail to detect landmines made with minimal or no metal content. Additionally, while thermal imaging and drone-based surveys can cover larger areas, they lack intelligent analysis capabilities and are easily affected by environmental noise and temperature variance, resulting in inconsistent and unreliable detection. Overall, current system struggles to balance safety, accuracy, and efficiency, making them insufficient for real-world demanding demands. Coming to the proposed system or base paper work, the proposed system uses thermal drone imaging combined with deep learning to provide a fully automated and more reliable approach to landmine detection. In this method, drones equipped with thermal sensor captured detailed temperature patterns from the ground, allowing the system to observe variants that may indicate buried landmines. These thermal images are then analyzed by convolutional neural networks or similar AI models that have been trained to recognize the subtle differences between actual landmine signatures and natural environmental features. By automating both data collection and detection, the system significantly reduces the need of human involvement in dangerous areas, improves detection accuracy across different weathers and soil conditions, and enables fast scanning for larger terrains. Overall, it offers a scalable, intelligent, and safer solution compared to traditional landmine detection techniques. Coming to the dataset used in this project is test images of buried landmines, consisting of both thermographic and visible spectrum images captured using a drone-mounted thermal camera system to observe landmines buried at depths of 0 to 10 centimeters. It is designed for automated mining detection through thermal contrast analysis, as buried mines and surrounding soil exhibit different heating and cooling patterns, making it suitable for tasks such as classification, segmentation, and object detection. For the YOLO detection branch, each image includes a .txt annotation file in YOLO format with normalized bounding boxes, coordinating and class identifiers for all visual mines. The dataset contains variations in terrain, lighting, occultations, and mine visibility. providing a robust resource for training machine learning and deep learning models to accurately detect and localize buried landmines under realistic field conditions. Coming to the novelty or extension or enhancement or improvement. As an extension, the advanced deep learning architecture such as exception and a hybrid model combining exception and ResNet 50 were implemented to analyze the thermal drone image dataset. These models are known for their strong feature extraction capabilities, especially in identifying subtle visual patterns. By training and evaluating these models, the system achieved an unexpected 100% accuracy, demonstrating their effectiveness in distinguishing landmine-related anomalies for normal terrain. In addition to classification models, the YOLO family of object detection models was incorporated to detect abnormalities directly within the images. YOLO provides real-time detection capabilities, enabling the system not only to classify images but also to pinpoint the exact location of the suspicious object within thermal frames. Furthermore, to make the system accessible and user-friendly, a Flask-based web interface was developed. This interface allows users to upload images and instantly receive predictions from the trained models without requiring technical knowledge of deep learning or command line operations. The integration of Flask ensures smooth interaction between the user and the AI system, enabling practical deployment and real-time testing. Together, these extension points greatly strengthen the overall project by improving accuracy, enhancing detection capabilities, and providing an intuitive platform for user interaction. Coming to the flow of the work, first, we need to import the packages. We need to import all the necessary Python libraries required throughout the project. It includes packages for data handling, image processing, visualization, deep learning frameworks, and YOLO specific libraries. The goal is to ensure all functions, models, and pre-processing steps can be executed without interruptions. A well-defined import block also improves readability and reproducibility when sharing or deploying the project. Next, data preparation. This module focuses on collecting, organizing, and preparing the landmine dataset. For the classification branch, images are assigned class labels and stored either in label-specific folders or annotation files. For the YOLO branch, each image must have a corresponding .txt annotation file containing bounding box coordinates in YOLO format. This stage ensures that both classification networks and YOLO detection models receive clean, consistent, and model-ready dataset structures. Next, data visualization. Visualization is used to understand your dataset before training. This module includes generating bar graphs that displays the number of samples per classes, helping identify imbalanced dataset. It also shows sample images with their labels or bounding boxes to confirm annotation quality. Visualization acts as an early debugging tool to verify that pre-processing, labeling, and bounding box coordinates are correct before training begins. Next, pre-processing. This model prepares images for deep learning models. For classification pre-processing, images are resized, converted to float 32 and normalized, then transformed into NumPy arrays or tensors. Feature extraction uses pre-trained models may be applied to generate embeddings for machine learning classifiers. YOLO pre-processing. Pre-processing includes creating a data.yaml file, specifying dataset paths and class names. YOLO expects images and corresponding label.txt files to be structured in a particular directory format. This module ensures that both classification and YOLO pipelines receive consistent pre-processed inputs. Next, model training. This model involves training two branches. One, classification branch, and two, extension YOLO classification or detection. In classification branch, transfer learning models such as VGG19, Inception V3, ResNet 50, MobileNet V3 large, and exception receives pre-processed images, and learn to classify whether a landmine is present. Hybrid models combine strengths of multiple architectures for better accuracy. YOLO-based classification, YOLO V5, YOLO V8, and YOLO V11, YOLO V5, YOLO V8, and YOLO V11 are trained to detect and localize landmines. YOLO learns bounding box prediction and class probability simultaneously, providing both detection and classification capabilities. This stage results in models capable of locating and identifying landmines regions in images. Next, evaluation. This module measures the performance of trained models. Classification models are evaluated using accuracy, precision, recall, F1 score, confusion metrics, and ROC-AUC curves. These metrics indicate how well the model distinguishes between classes. YOLO models are evaluated using MAP, precision, and recall to access detection or localization ability. This stage helps compare different architectures, determine which performs best for landmine detection tasks. Next, interface pipeline. This module defines how the train system operates on new, unseen land images. An input image goes through the YOLO model first to detect and draw bounding boxes around potential landmine regions. Simultaneously, the classification model predicts whether a landmine exists in image or classifies its type. The output includes the processed image with bounding boxes, predicted classes, and confidence scores. This pipeline integrates detection and classification into a single user-ready interface system. Next, Flask web app. This module deploys the trained model through a web interface. The frontend provides an upload from where users submit land images. The backend loads the trained YOLO and classification models, perform detection and classification on the uploaded images, and returns results. Users see the output image with bounding boxes, predicted classes, and confident values directly in the browser. This allows real-time use for the system without requiring technical knowledge. The algorithms used in the project are BGG19, Inception V3, ResNet 50, MobileNet V3, large. Extension models are Exception, Hybrid model, which includes Exception plus ResNet 50. And as an extension, we also applied YOLO family. We used YOLO V5, YOLO V8, and YOLO V11. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute this project first, we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. .ipynb files. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the project execution. Firstly, You need to copy the path of the code folder from the address bar of the File Explorer. Then open Anaconda prompt. Use the command cd followed by a space and paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. So, the home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have Home button and Get Started button. Now, click on Get Started button so that the log on HTML will be opened. Here, we need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a password. Then click on Create an account so that all the given details are stored in signup.db and the login.html will be opened, where we need to access the application by username and a password. Then click on Sign In so that the prediction page has been displayed. In this page, we have Predictions button, Data Visualization button, Notebooks button, and Logout button. So firstly, click on Predictions button. Here, as we are doing both classification and detection, we need to check one by one. First, we will go with classification so that the image upload for classification will be opened, where you need to upload the image and then classify the image. Firstly, we need to upload the image, then click on Classify Image. So the given input image is pre-processed and the output will be displayed as Landmine classification. This is uploaded image. This is a prediction results. The confidence score is 99.99%. Here we have the result information like landmine is detected and the safety recommendations are given and model analysis is also given. Now let us click on upload new image. As we have checked for landmine, now let us check for no landmine. The given input is uploaded. Click on classify the image. The image is pre-processed and the output is displayed as no landmine. The confidence score is 99.97%. We also have the result information like it is a safe area and the classification details and the model analysis. Now, let us click on prediction button and check the detection part. When you click on the detection, again the input image will be opened. We need to upload the image from the detection part. Choose an image from the test cases of the code folder. Then click on detect image so that the input image is pre-processed. The detected images is shown here and the detection result is given as detection completed. One object has been detected. With the boundary boxes, the detection place has been highlighted. Here we have the detection results and the detection information. Now, let us click on data visualization so that the graphical representation of the project will be opened. First, we have the classification graph and next we have the detection graph. So let us check one by one. First, we have number of images per class graph. The bar chart illustrates the distribution of images across two classes, landmine and no landmine. It shows that there is a significant imbalance in the data set. The landmine class contains 452 images, which is more than 4 times the number of images in the no landmine class, which has only 108 images. This indicates that the majority of the images in the dataset despite landmines, while a smaller portion represent areas without landmines. Such an imbalance could have important implications for trained machine learning models, as the model might become biased towards the more frequent landmine class. The graph clearly emphasizes that The need to consider strategies for handling class imbalance such as data augmentation or resampling to ensure fair and accurate model prediction. Next, we have confusion matrix and ROC curve graph. The confusion matrix on the left shows that the hybrid ensemble model achieved perfect classification performance on the test set. It correctly identifies all 87 landmine insights and all 25 non-landmine insights with zero false positive or false negatives. This indicates the model made no misclassification. The ROC curve on the right supports this results because the model separates the two classes perfectly. The ROC curves raises straight to the top left corner, producing an AUC of 1.00. An AUC of 1.00 represents ideal discriminatory ability, meaning the model can flawlessly distinguish between landmine and no landmine cases. Next, we have accuracy graph. The bar chart compares the accuracy of several machine learning models used for classification. Among the individual deep learning models, Exception and ResNet 50 performs the best. Both achieves very high accuracy close to 1.0. VGG19 and Inception V3 shows noticeably low accuracy, indicating they are less effective for this task. MobileNet V3 Large performs moderately well with accuracy higher than VGG19 and Inception V3, but still below the top performance. The hybrid ensemble model stands out as the best overall, reaching perfect or near perfect accuracy, demonstrating that combining multiple models lead to superior and more reliable performance compared to any single architecture. Next, we have F1 score graph. The bar chart illustrates the F1 scores of various machine learning models, showing how well each model balances precision and recall. Among the models, Exception and ResNet 50 achieves the highest F1 scores, indicating strong and consistent performance in correctly identifying both positive and negative classes. The hybrid ensemble model performs at the top, reaching a perfect or near perfect F1 score, which demonstrates that combining multiple models leads to more robust and reliable predictions. MobileNet V3 Large shows moderately strong performance, while VGG19 and especially Inception V3 have noticeably lower F1 scores, suggesting they struggle more with balanced classification. Overall, the graph highlights that ensemble and advanced architecture significantly outperform the older or simpler models. Next, we have recall graph. The bar chart compares the recall scores of several machine learning models. Recall measures how well a model identifies all relevant positive cases. So, higher values mean fewer false negative. From the graph, Exception ResNet 50 and hybrid ensemble models achieve the highest recall, all close to 1.0%, indicating they almost perfectly capture the true positive in sales. MobileNet V3 Large performs moderately well with a recall around 0.78%, while VGG19 follows with roughly 0.62%. Inception V3 shows the lowest recall at about 0.55%, suggesting it missed more positive cases than the other methods. Overall, the plot highlights that the ensemble and deeper architectures provide superior recall performance compared to the older and lighter models. Next, we have precision graph. The bar chart illustrates the precision scores of several machine learning models, showing how accurately each model identifies positive predictions. A higher precision means the model produces fewer false positive. From the graph, ResNet 50 and the hybrid ensemble model achieves the highest precision, both reaching 1.0, indicating they almost never mislabel negative cases as positive. Exception also performs very strongly with a precise close to 0.95%. MobileNet V3 Large and VGG19 shows moderately high precision at around 0.89 and 0.85 respectively, indicating reliable but not perfect accuracy. Inception V3, however, has the lowest precision about 0.64%, suggesting it makes more false positive predictions compared to the other models. Overall, the graph highlights that deeper architectures and ensemble methods deliver superior precision performance. Now, coming to the detection graphs, first we have YOLO precision graph. The bar chart presents the precision scores of three YOLO model versions, YOLO V5, YOLO V8 and YOLO V11, showing how accurately each model identifies positive predictions. YOLO V8 achieves the highest precision around 0.73%, meaning it makes the fewest false positive errors among the three models. YOLO V5 follows with a precision of about 0.67%, indicating reasonably strong accuracy, but still slightly less precise than YOLO V8, YOLO V11, and shows the lowest precision at roughly 0.50%, meaning it misclassifies more negative in saints and positive compared to the other models. Overall, the graph clearly highlights that YOLO V8 provides the best precision performance, while YOLO V11 performs the weakest in terms of precision. Next, we have YOLO recall graph. The bar chart compares the recall performance of three machine learning models, YOLO V5, YOLO V8, and YOLO V11. Recall measures how well a model identifies all relevant objects, so higher values indicates fewer misdetections. In the graph, YOLO V5 and YOLO V8 performs almost equally, each achieving a recall slightly above 0.73%, showing strong ability to detect most of the true objects. YOLO V11, however, lags behind with a recall of around 0.45%, indicating it misses a large portion of relevant items compared to the earlier versions. Overall, the visualization makes it clear that YOLO V5 and YOLO V8 outperform YOLO V11 in terms of recall for this particular evaluation. Next, we have YOLO MAP graph. The bar chart illustrates the mean average precision scores of three machine learning models, YOLO V5, YOLO V8, and YOLO V11. MAP is a key metric for measuring all over detection accuracy, combining both precision and recall. So, higher values represent better object detection performance. In this graph, YOLO V8 achieves the highest MAP, slightly above 0.75%, indicating it delivers the most accurate detections among the three. YOLO V5 follows closely with a MAP just above 0.72%, showing strong and reliable performance as well. In contrast, YOLO V11 performs slightly worse with a MAP around 0.40, suggesting that it struggles to accurately detect and classify objects compared to the previous versions. Overall, the graph clearly highlights YOLO V8 and the best performing model with YOLO V11 showing a notable drop in accuracy. Now click on Logout. So finally, this project presents an AI-powered landmine detection system combining thermal drone imaging with deep learning models. Advanced classification models and YOLO-based detection accurately identify and localize landmines, minimizing human risk. The system processes larger areas quickly and performs well in varied terrain and environmental conditions. Deployment via a Flask web app enables user-friendly predictions. Overall, the approach enhances the speed, safety, and reliability of demanding operations, offering a practical solutions for post-conflict regions. This is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.